So hello everyone, good morning. First of all, thanks for having me here today in this talk. We will present some of our numerical investigations regarding the blade resolved CFD simulations of the NREL 5 megawatt baseline wind turbine that we have been modeling considering a solver investigation. Our group is composed by me, Marielle, Rodolfo Puraca, my colleague, and our supervisor and group coordinator, Dr. Bruno Souza Caro. In the introduction section, we will explain shortly about our motivation to develop this research, in addition with the main objectives and the research contributions in the methodology. We will explain how we conduct the solver investigation in the OpenFOAM software. In the sequence, we talk about the steps considered to perform all the numerical simulations, such as the computational domain dimensions and its boundary conditions. Also, the strategy considered for the spatial discretization, the numerical schemes considered to discretize each operator of the Navier-Stokes equations, and the solver information applied in all the simulations. Last but not least, we will present our results and the concluding remarks. Up to now, since the first blade resolved simulation of a wind turbine rotor's blade, an extensive number of CFD investigations regarding the rotor-only simulations have been made. However, when considering the wind turbine rotor's blade in addition with the nacelle and tower geometries of a megawatt scale wind turbine, in the CFD simulations, more efforts to optimize the computational costs of the numerical modeling must be made. So the target of our investigations is to predict the aerodynamic loads and the overall wind turbine performance of the baseline NREL 5 megawatt wind turbine for offshore applications, of course, in full scale, considering the operation condition of optimal wind power conversion efficiency. Figure 1 illustrates the case being investigated in this research, which includes a wind turbine in a full scale of 5 megawatt under a logarithmic non-turbulent wind profile. The main, just a moment, yeah, here. All the numerical investigation which will be presented were carried out in the open source OpenFOAM software, where the CFD simulations were performed considering the finite volume method. As the problem being investigated is incompressible, among the pressure-based solvers options to treat the pressure velocity coupling problem, we choose the iterative approach of the PISO algorithm to conduct the analysis, which in OpenFOAM is achieved through the pinball solver utility by changing the any character from 1 to 2 in the solver dictionary. The iterative approach has advantages since for each time step the algorithm solves the pressure corrections twice until reach the desired tolerance. However, in this work, since the mesh considered in the CFD investigation is dynamic, besides the normal turbulentity correction and extra correction for the flux which cross the mesh cell's face, is also considered to verify its influence in the results accuracy and computational costs as well. Therefore, figure 2 presents the two forms of the PISO algorithm which were investigated in our research. In letter A, the generic form, and in letter B, considering the phase flux correction. The main difference between the two approaches is concentrated in the first steps of the algorithm, hereby considering the phase flux correction as presented in figure 2A, letter B, an extra correction for pressure considering the phase velocity UF from the previous time step is performed before the start of the iterative PISO steps. Besides the solver investigation, a time discretization procedure were also conducted by considering different CFEL values for the convergence parameter, by limiting the current number in the simulation solver dictionary in order to capture, we limited that by limiting the current number in the simulation solver dictionary in order to capture which time step sizing was more appropriate to capture adequately the transient effects of the problem. Lastly, as a verification procedure, the CFD results were benchmarked against the results obtained through the OpenFast code, considering the same NREL 5 megawatt wind turbine and the same environmental conditions. As the main objective of the CFD simulations was to predict the performance of the NREL baseline 5 megawatt wind turbine, considering the power losses, blade loading, and weighty aerodynamics pattern under the tower influence, the full wind turbine geometry, which includes 3 blades, the hub, the tower, and the nacelle parts, were built in the solid edge software and imported to OpenFOAM, where all the other parts of the computational domain were built. As presented in Figure 3, where its dimensions were 500 meters wide, 300 meters high, and 600 meters long. The boundary conditions for the velocity at the inflow region were at the Dirichlet condition as a prescribed logarithmic profile, where at 80 meters high, the velocity was 10 meters per second. In Figure 4, we present the strategical partition of the computational domain that we consider it to apply different mesh refinements according with the complexity of the flow in each region. The mesh obtained through the strategical partition were composed by about 21 million cells. Figure 5 presents some images of different regions of the mesh, which is composed by elements of the size of 1 millimeter close to the blade's wall, 1 centimeter close to the tower wall, and 8 meters in the far field region. Regarding the spatial discretization schemes considered for the Navier-Stokes equations operators, the treatment of the divergent terms was made through the second order opulent scheme. In addition, central difference scheme was considered for the Laplacian terms, and last square cells-based scheme for the gradient terms. Last but not least, the set of linear equations were solved by the linear solver geometric algebraic multigrid solver for the symmetric matrices, and Newton Krylov solver connected with Diu preconditioner for the non-symmetric matrix. About the temporal discretization scheme, the second order backward scheme was considered in implicit form in all the analysis, and the turbulence were treated by the Urans approach along with the K omega SST turbulence model. Regarding the solver information for the time discretization investigations, the CFL numbers considered were equals to 1, 2, and 4, and all the estimated variables in all the simulations achieved 10 in the minus 6 of tolerance in each simulation case. All of our CFD simulations were carried out in the Brazilian supercomputer Santos Dumont, where the mesh was patterned in 240 subdomains using a Scotch decomposition. So now I give the word to my colleague Rodolfo to proceed with the presentation.
Good morning or afternoon to all. I will present the results and the discussion of NREL wind turbine CFD simulation. Here are plot the power and the thrust outputs. In black is the iterative piso in its generic form, and in blue the iterative piso with flux correction. Both cases were simulated with CFL2 and are compared against the OpenFast result in the gray line. Analyzing this graph, it can be noted, although the mean value is close for the power and thrust, the signal from the piso in generic form is noisier than the piso with flux correction for both the power and the thrust. And the simulations uses a non-turbulent wind profile as in flow. So this noise can be seen as a numerical instability caused by a numerical arrangement, which is not wanted for a simulation that in the future will be used to analyze turbulent wind profiles. Next slide, please. Here we have plotted the graphs of the distributed force along the blade span, comparing the piso in generic form in black and the piso with pressure correction in blue and the open fast in gray. This shows that when the blade is in the highest position, the azimuth angle 0 degrees, the difference between CFD results and open fast are small. But when the blade is at lowest position at the azimuth angle of 108 degrees, experience the tower interference, the results in the distributed forces along the blade are more different, showing the CFD result larger normal and tangential forces. Next slide. Then we show the computational cost comparison between the use of the iterative piso in generic form and with the flux correction. And we can see that the piso in generic form is less expensive than the piso with the flux correction. Seeing the first plot that shows the execution time of each iteration. But when we see the second graph that showed the total execution time to complete 1 second of simulation, this difference is very small, having the piso in generic form lasts 10 hours and 48 minutes and the piso with flux correction 11 hours and 16 minutes. It's important to remember that the piso with the flux correction gave a better and smooth power thrust result signal, adding a little in the computational cost of the simulation. Next slide. Here we show the results of the simulation comparing different CFR numbers, 1 in yellow, 2 in green, and 4 in red, again to the OpenFast result in gray. From the graphs, it can be seen that with the increase of CFL number, the power and thrust is overpredicted, and this is caused by difference in the simulation's result fields that will be shown forward in the presentation. It's important to note too that the power and thrust when using CFL1 starts to oscillate even in the steady region due high instability when compared to the results using CFL numbers 2 and 4. Next slide, please. We show in this slide the results of the distributed force along the blade span comparing different CFL numbers. Again, the normal and tangential forces are more different from the OpenFast results when the blade is at lowest position at a smooth angle of 180, where from 0.5 span, the normal and tangential forces are greater than calculated by OpenFast, decreasing for the same level at the tip of the blade. High CFL numbers, as shown in the previous slide, overpredict the forces, as shown here too. Next slide. In these slides, we show the comparison of the flow characteristics for the simulations using CFR numbers 1, 2, and 4. In the figures A, B, and C, we show the axial velocity isocontour, and we can see that with the increase of CFL number, the velocity gradient in the wake is larger, showing that the wind turbine is extracting more energy from the wind, what explains the high prediction in power and thrust previously shown. Other characteristic observed is the behavior more unsteady of the wake in lower CFL numbers, such as CFL1. The figures D, E, and F show the isosurface of Q parameter of value 0.05 colored by vorticity magnitude. This shows that with the higher CFL number, decrease the formation of the vertical structures, reinforcing the results of power thrust plots, because with less formation of vertical structures, more energy the wind turbine can extract from the wind. Next slide. Here we quickly show the results of the slides at region of the blade and tower interference at high 550 meters above the ground, showing the axial velocity. And from this plot, it's not possible to see clearly difference using different CFR numbers. But at the figures J, K, and L enforces that with higher CFR numbers, the vorticity structures are decreased, as shown in the vortices formed in the tip of the blade and formed by the tower. Next slide, please. Then we show the computational cost comparing different CFR numbers. As expected, the higher CFR number leads to a faster simulation, as observed in the graphs, and show the importance of choosing a value for the CFL parameter, because it impacts severely in the computational time. Having the simulation with CFL1 last complete 1 second of simulation time, 29 hours and 33 minutes, CFL2 12 hours and 46 minutes, and the CFL4 6 hours and 18 minutes. Next slide.
Okay, so to conclude our presentation, first, a comparison of the NREL 5 megawatt offshore wind turbine generated thrust power production and forces distribution along the blade span obtained through two different approaches of the iterative piezo algorithm were presented, along with the results obtained in the NREL OpenFast code. And both methodologies show similar results. However, when the approach, considering the phase flux correction, the algorithm presents a more stable convergence behavior without any significant impact in the computational costs. Secondly, a time discretization investigation were carried out considering CFL numbers equals to 1, 2, and 4, and the increase in the CFL number changed the gradient of the axial velocity significantly in the wake region, In addition, the discrepancies between the CFD and OpenFast results for the prediction of the distributed forces were more significant when the tower were crossing in front, when the blade of the wind turbine were crossing in front of the tower, due to the transient effects caused by the tower influence. Also, with CFL number equals to 4, reduction in the axial velocity caused by the blade was higher, which resulted in the overestimation of the wind turbine power, thrust, and forces distributions along the blade span. Therefore, by considering the temporal discretization investigation employed in the analysis, the accuracy and the performance results were better predicted by the numerical model considering lower values of CFL numbers. However, when comparing CFL numbers 1 and 2, a higher difference in the computational cost was found. CFL equals to 1 have a computational demand twice the CFL number equals to 2. So the better option here will depend of the computational demand available to perform the simulations. But both results were acceptable. So this is it. Thank you for your attention, and we are open to questions now.